Calculus 2, Section 5.6, Substitution and the area between curves. We can evaluate the definite integral with the limits of integration, that's what makes it a definite integral, by extending the substitution process to the limits of integration. So, as an example, what is the integral from a negative square root of 7 to 0 of t times the quantity t squared plus 1 to the 1/3 power dt? Well, we're going to do a substitution. I want to let u equal that t squared plus 1 stuff in here. So du equals 2t, then that's 0 dt. So now you look over here. Now you don't have the 2, so I'm going to make this a 1/2 du equals t dt. And so I've got the dt and the t. I got that taken care of. Use t squared plus 1 and then the exponent of 1/3. So this becomes the integral. Let's not put the limits on there yet. But the t dt is the du. I'm sorry, it's the 1/2 du. And t squared plus 1 is u to the 1/3. So now I've got that substitution, but we're going to extend that to also the limits. If u is t squared plus 1 and t is the negative square root of 7, the lower limit, u is equal to this negative square root of 7 squared plus 1. So this is, when you square a negative, it's a positive, and the square root of 7 squared is 7. So we get 8 for that lower limit. The upper limit, u is equal to 0 squared plus 1. I guess I don't need the parentheses. So this is just 1. So this now goes not from a negative square root of 7 to 0, it goes from 8 to 1. Now you could substitute in and then go get back to the t's and use this negative square root of 7 and 0. But if you just need the answer, just need the number, you might as well change the u limits of integration also. So first of all, we're going to add 1 to the exponent. That's u to the 4/3. And then dividing by that new exponent, dividing by 4/3 is really multiplying by 3/4. And this is evaluated, let's put this here, from 8 to 1. And then we'll multiply by the 1/2. So 1/2, let's see. If we plug in a 1, 1 to any power is 1, so this becomes 3/4. Minus, now we're going to plug in an 8. Let me write it down first. 3/4 times, this is going to be an 8 to the 4/3. Well, let's see, we have the 1/2. We have the 3/4. Gotta fit this in here, so I'm going to have to do. Doing cube roots first can be helpful. That gets you to smaller numbers if it's nice. The cube root of 8 is 2. And then 2 to the 4th is really 16. So this is minus 3/4 times 16. So now we get 3/4 times 16 over 1. This 4 goes once and 4 times. So it's 3/4 minus this 12. Well, let's take half of these, I guess. Half of 3/4 is 3/8. And half of 12 is 6. So you take a negative 6 and you subtract just a moment. So a negative 6 and a positive 3/8 is negative 5 and 5/8, or it's negative 45/8. Squeeze that in barely. Now, how do we know that that's going to be the answer? I guess we can take a look at the graph, but the graph is a cube root, which is negative to the left of the y-axis. So at least it makes sense that way. What could we have done if we didn't want to do that extended substitution? Well, we could have figured it out a little bit differently. Let's see, this was the integral from a negative square root of 7 to 0 of t times t squared plus 1 to the 1/3 dt. We did those substitutions. Let's not do the lower and upper limits. Let's just do that 1/2 u to the 1/3 du. So now we're going to say this is 1/2 u to the 4/3 times the 3/4 plus some constant c. We can substitute this back. So we're going to put in for the u, the t squared plus 1. So we can multiply these two together, I guess, and put them together. That's 3/8. And instead of u, it's t squared plus 1 to the 4/3. And now we can evaluate this, negative square root of 7 to 0. Because we're back into the t variable of integration. So this becomes the 3/8. T is 0 squared plus 1 to the 4/3 minus the 3/8. T is negative square root of 7 squared plus 1 to the 4/3. So this is really just 1, and this is then just 3/8. This is the same thing we sort of did. Square that negative, it's positive. Square the square root of 7, it's 7 plus 1 is 8. So it's a negative 3/8, 8 to the 4/3. Take the cube root, you get 2 to the 4th power, and you get 16. So you get 3/8 minus 3/8 times the 16, or this goes once, this goes twice. There's your 3/8 minus 6, and we ran out of room again, but you can take it from there. So it doesn't matter if you extend the substitution so that the u will take care of these limits, or we substitute back into the beginning variable, in this case t, and then use those limits. One way or the other, you should get the right answer. So what is Theorem 6? Substitution in definite integrals. We can evaluate the definite integral. Oh, I'm sorry, that's not what I want. That's before. If g prime is continuous, So if the derivative of g is continuous on this interval, from closed interval from a to b, and f, little f, is continuous on the range of g, then the integral from a to b of f of g of x times g prime of x dx. So this is where we've got that function. This is the t squared plus 1, and this would have been the 2t, and f then would have been to the 1/3 power. What do you suppose this equals? Well, it's the same integral, but we're going to use f of u du, and we can't use a and b, we've got to use g of a to g of b, because we're using the u in that, which is like the g in this case. We're just extending our substitution. Okay, what about definite integrals of symmetric functions? Done it again. Just a moment. Try this once more. Definite integrals of symmetric functions. So if you have a symmetric function with respect to y, that means that whatever's over here has a mirror image over here. And so if we find the area, and we're going from, say, negative a to positive a, then we may double the area. If we have something like this, we may cancel the area. So there's some things, if we know the function is symmetric, we can make some things a little easier. There's a theorem. Theorem 7. Let f be continuous on the symmetric interval from negative a to positive a. That's negative to positive. There are a couple parts. If f is even, like our first example here when we had x squared, that's an even function, symmetry with respect to the y-axis, then the integral from a negative a to the a of f of x dx is 2 times the integral from 0 to a of f of x dx. We added these two together. They're both the same, just doubled it. Part B, if f is odd, An odd function was like the cubic that I was drawing here. That's what I was trying to draw. It has symmetry with respect to the origin. Then we know that the integral from negative a to a of f of x dx cancels, and it's 0. So, sometimes you'll be able to know that because you know what the functions are. Sometimes you won't. Just be aware that if you come up with a 0, then you might have canceled things completely. For example, the integral from a negative 2 to 2. X times the square root 4 minus x squared dx. When you see this negative 2 to 2 stuff, you should start wondering, but I don't think that's obvious here. So let's see if we can then just keep on going and figure it out. What you might do is see if you can draw the graph. If nothing else, if you're allowed to use it, you should use your graphing calculator. Let me pull up mine. I got this cheap TI-83, but cheap or not, it does the job. So let's clear this out. Y equals, let's see, that was x times the square root. Oh, let's clear some of these others out too. So x times the square root 4 minus x squared. That should be it. We're going from a negative 2 to 2, so I'm going to make my window a negative 2 to 2. And then I can do a zoom fit and see what this thing might look like. Now, this doesn't prove that this is symmetric with respect to the origin. You might have to check what f of negative x is. It should come out to be a negative f of x. But you can see quickly here that I might be getting a 0 in my answer. So let's draw this in. So that we know what we're looking at. Can always help. So if they just want the definite integral, they want the number associated with this area. And this negative and positive area is probably going to just be a 0. If you want to check that, we can do that. We can go from a negative 2 to 2, but let's use a substitution. 4 minus x squared. So du is negative 2x dx. Let's see, we've got, put that negative 2 out front. So, I'm sorry, negative 1/2 out front. Because the negative 1/2 du is the x dx. And that's what we have here, the x dx. And this is u, the 4 minus x squared, to the 1/2 du. So, the integral, we need the limits of integration. 4 minus, the lower limit is a negative 2 squared. So, it's really 4 minus 4, or 0. The lower limit, that's the lower. This is the lower, this is the upper. So, it is 4 minus 2 squared, which is also 0. And the integral from 0 to 0 is pretty easy to calculate. It's 0. So, you may not know this is symmetric, but if you do a substitution and you get something like this, this is always 0. Because you can't have any area under that curve. If you were asked to find the total area, we still use this substitution, But now, because we know we go from, like you can do a 0 to 2, if we plug in a 0, we know for the lower limit, let's do that. U is equal to 4 minus 0 squared, or U is 4. If we go from 0 to 4, well, it's not going to be 0. Plug in a 0 for this lower limit and go from 0 to 2. We're going to use 4 for the lower limit. When we plug in a 2 for the upper limit, then we still get 0. So this is going to be a negative 1/2 integral from 4 to 0. But if we want the total area, like totally, we're going to double this, right? And this is still going to be u to the 1/2 du. So this almost cancels. It's a negative 1. And this is going to be, add 1, so you get 3/2, multiply by, or divide by the reciprocal, or multiply by the reciprocal, divide by 3/2. So it's 2/3 u to the 3/2. And we're going to evaluate this from 4 to 0. Plug in a 0, you get 0. Plug in a 4, take the square root first, that'll give you 2, cube it, that'll give you 8, 2 times 8 is 16, but remember the lower limit, we're going to subtract that, and with that negative, going to be, so this is now 8 times 2/3, or 16/3. So each of these, I guess, is 8/3. Add them together to get the 16/3. But the definite integral, if they don't ask you for area under the curve, is 0. Because those areas cancel. So, recall, remember for a definite integral, if that's what they want, the definite integral, that equals some number. Just call it, I don't know, C. If we want the area, then we've got to figure out perhaps where things become positive and negative. So we might have to add up some areas. And maybe make the negative area positive so we can add them and not subtract them. Now we're going to talk about area between curves. We're going to talk in a theorem only about when one curve, call it F, is greater than another curve, call it G. If it's not, then we need to essentially do like we did with the areas. And if they cross, these two functions cross each other, then we're going to have to sort of split this into intervals and figure out each of these areas individually and then add them up. But the definition that they have for area between curves, if f and g are continuous, with, and here it is, f of x greater than or equal to g of x, on that interval from a to b, throughout that interval, then, yeah, let's put this here, I guess, the area of the region between y equals f of x and y equals g of x from a to b is the integral of f minus g from a to b. So the integral from a to b, that's a b, is f of x minus g of x dx. We're just going to take this area for f and subtract the area under the curve for g to get the area in between. How about an example? We've got this graph. This graph looks something like this, and this one looks something like this. This graph is x cubed. This graph is x equals y squared. This is y equals x cubed. So we want the area between, and we need to find this point here too. So this is the only one that they're worried about. Where do they cross? Well, x equals y squared is a little bit backwards. So we're going to say square root of x equals y. Now you got to be careful. This is positive because it's this upper side. If we're down below, it would be negative square root of x. But in this case, we can use this one. So they're both y equals. So we want the integral. Okay, where do they cross? I guess we need to find that out. When does x cubed equal square root of x? Well, if we square both sides, we get x to the 6th equals x. And if we, it's tempting to divide both sides here. Don't do it. Subtract x to the 6th minus x equals 0. Because then you should factor this. We can factor out an x. This is x to the 5th minus 1 equals 0. And now you don't lose a root. If you would have divided by x, then you would have just gotten the x to the 5th stuff and a 1. But now we also have an x equals 0, and you would have lost that root. So be careful. Dividing by a variable is very dangerous. So if we get x to the 5th minus 1 equals 0, or x to the 5th equals 1, x has got to equal 1. Not plus or minus here. This is an odd exponent. So they cross at, as we could see here, 0 and 1. So this is a 1 over here also. So we want the area between, we have to go from 0 to 1. And we want the f, the one above, which is the square root of x, minus the one below, which is x cubed dx. Now we can do these individually. The area from, or the integral from 0 to 1 of square root of x dx minus integral from 0 to 1 of x cubed dx. So this is x to the 1/2, so it's 2/3 x to the 3/2 evaluated from 0 to 1. We had that in that last problem, I think, or something similar. Here we add 1, and we divide by the new, so it's 1/4 x to the 4th, and that is from 0 to 1. Plug in a 1, it's really nice, times 2/3, so it's just 2/3. Minus, plug in a 0, you just get 0. Minus, plug in a 1, 1s are sort of nice, this is just a 1/4. Minus, plug in a 0, you just get 0. So it's really 2/3 minus 1/4, which is, the common denominator is 12 multiplied by 4, 8/12 minus multiply by 3, 3/12. So you get 5/12. That's the area between the two. Now, this gives us an opportunity to integrate with respect to y instead of x. So on the next screen in a different color, in a lovely shade of yellow, we're going to do the same thing. This is maybe a yellow lime green. So we're going to integrate, because we have the square root of x. This was really x equals y squared, the way we had it written. And this was y equals x cubed, or what does x equal then? The cube root of y. So if you've got both of these solved for x, you can still find this. The nice thing is it still goes from 0 to 1, but it's on the y-axis. And now this is the larger, in a sense, function because it's further to the right. Just like the square root was higher vertically, this is further to the right. So we're still going to take an integral from 0 to 1, but now we're going to do this x, which is y squared, minus the cube root of y to the 1/3 dy. So you can do this with respect to y instead. Split that up, integral from 0 to 1 of y squared dy, minus the integral from 0 to 1 of y to the 1/3 dy. So 0 to 1, this is y cubed over 3, 0 to 1, minus, add 1, so it's 4/3. You got 3/4 y to the 4/3, 0 to 1. So plug in a 1, 1s are nice. This is 1/3 minus, plug in a 0. And then we're going to subtract, plug in a 1. This is 3/4 minus 0. So this is really 1/2 minus 3/4. Now does that look right? Well, I made a mistake. This this is that graph, which is below. So I've got these backwards, first of all. So let's see, we're doing the same thing, except we need the 1/3 first. So if we have y to the 1/3 and add 1, it's 4/3. And times 3/4. So this is really backwards. And then I made a second mistake over here. This is not 1/2. Plug in a 1, we get 1/3. So this should be 1/3. And these should be switched. So it's 3/4 minus 1/3. Oh my gosh. This is why you check your work. Huh. So 3/4 as 12ths, and multiply by 3, we get 9/12, minus multiply by 4, we get 4/12, which is 5/12. And it also goes to show you that doing it with respect to y can be a little more confusing, because I'm used to, as you probably will get to, we're thinking of this vertically instead of horizontally. This is the upper one, and I even marked it, but that's not the y squared, x equals y squared, that's the x equals cube root of y, that squiggly one. And you should get the same answer either way as we did once we switched that and got the right numbers here. Anyway, we would come up with a negative, and you know that that area's got to be positive. Just like above, to the right of the y-axis is positive, to the left is negative. The same idea. Okay. Now we're going to do some examples. This is number 16, page 301. Here's going to be the u sub, right? So we're going to let u equal that 1 plus the square root of y. So du, well, for a constant at 0, this is really 1/2. So add 1, you get 3/2. Divide by the new, you get 2/3 times y to the 3/2 dy. Well, over here, y to the 3/2. We have y to the 1/2. We don't have y to the 3/2. We don't have the 2/3. So we got the 2, but not the third. So I'm going to pull and multiply by 3. 3 du, and we get a 2y to the 1/2. We also have, if we pull out that 1/2, another y here, dy. So what do we do with that other y? How do we make that? Up here we also have, if you want to think of it this way, well, here I've done it again. We're taking a derivative here. So that's not correct. The derivative of a constant is 0. Y to the 1/2, here's when you take a derivative, you pull that 1/2 out front, and then you subtract 1 from the exponent. So this is a negative 1/2 dy. So let me scribble this out too. And so you got du is equal to 1/2, and you've got 1 over square root of y. So here's our 1 over 2 times the square root of y dy. So we didn't need this extra stuff. That's for a different problem. So u is this. So let's do our work here. Integral. So the dy and this 1 over 2 square root is just du. So I'm going to write the du. Our u is this 1 plus square root of y squared, but it's in the denominator, so it's really u to the negative 2. That'll make things a little bit easier. We need our limits of integration. See, since u is 1 plus the square root of y, and when we put in that lower limit, we put in, this is for the lower, we put in a 1, so we get 2. So the lower limit is 2. For the upper limit, you get 1 plus the square root of 4. They made it nice for us. So it's really 3. So we go from 2 to 3. So now when you take an antiderivative, you add 1, u to the negative 1, divide by that new power from 2 to 3. Plug in the 3 to the negative 1 over negative 1, minus plug in the 2 to the negative 1 over negative 1. This takes practice. Now you need more. So this 3 really needs to go in the denominator, and these negatives in the denominator just make the whole thing negative. So this is 1/3 negative. Minus a negative is going to be plus 1/2. And if we look at these as sixths, this is a negative 2/6, and it's a positive 3/6, so the total is 1/6. Does that make sense? Some neat substitutions. Double sub. How about another one here? Number 28. You want the total area. Now I forget if that had this in the book, but you can graph this pretty easily, I think. This is 1/2 integral from just a second. Oh, the function they give us. Y equals pi over 2 cosine x times the sine of pi plus pi sine x. So it's this times this, which includes as part of its argument a sine x. And when you graph that, you get back here to negative pi, and here to negative pi over 2, you get something like this. So if they want the total area, they know that these are probably going to cancel. And so you need to double this stuff, right? So I'm going to go from this negative pi over 2. Let me not write this yet. So I want the integral of pi over 2 cosine x times the sine of pi plus pi sine x dx. Now, we need a substitution here. This looks crazy. So, because of this cosine x and dx out here and this sine, I'm going to say that u is going to be the sine of x. So du, now let's be the pi plus pi sine x. So du, because this is a constant, will disappear, and this is pi cosine x dx. So, now I've got the pi, but I don't have pi over 2, and that's where that 1/2 came from before. So I'm going to need a pi over 2 and cosine x dx. So this needs to be a 2. I think I made a mistake here. Oh, I don't know. Okay. And that means this has got to be, if I need a pi over 2, this is going to be 2. But I'm going to have to pull out that 1/2. Okay, so let's put it down here. What about the other part? That's okay. We do need the 1/2 because this is just a pi and we need the pi over 2. So I needed an extra 1/2 here for this thing to work. What's a good way to say that? We have to multiply both sides by 1/2, I guess, is the way to do that. So that makes sense. So the pi over 2 cosine and the dx are taken care of with just the du, 1/2. Now, this sine of u is okay because u is going to be this pi plus pi sine x. So this is just the sine of u, and then du. So this becomes sort of an easy problem if you do the right substitution. So this becomes 1/2. Oh, we're going to do the limits of integration too. So u is pi constant plus pi sine. Now I'm going to go from a negative pi over 2 to 0, I guess. So I'm going to put in a negative pi over 2 first. So this is the lower. The sine of a negative pi over 2 is down here. This point is 0, negative 1. The sine is the negative 1, right? So this is really pi minus pi. This is a negative 1 times pi, or 0. We need for the upper limit, u is going to equal pi plus pi sine. That's going to be 0. Well, the sine of 0, this is 1, 0, is 0. So this disappears and we just get u equals pi. So now we're going to go from 0 to pi, sine u. Du. This is like writing with a pen. I guess it is a pen. So 1/2. What derivative did we take to get sine u? Well, we take the derivative of cosine to get negative sine, so we need a negative cosine u. And we evaluate that from 0 to pi. Now, we put in a pi. The cosine of pi is a negative 1, but take the opposite of that, positive 1. We put in a 0. Cosine of 0 is 1. But that's a negative 1. See, now, make sure you understand. We're subtracting the negative cosine of 0. So, cosine of 0 is 1. This would then be a negative 1, but we're subtracting it, so we get 2. And 2 times 1/2 is 1. Oh my gosh, all that work for 1. The answer to that whole thing. And it's easy to make mistakes. So one last problem. I've got a couple of choices. I'm going to do number 74. I want the area of the triangular region. And they put triangular in quotes. And they give us quadrant 1, bounded by the y-axis on the left. That's important. And on the right, both of these. Y equals sine x and y equals cosine x. So what the heck do they mean by that? Well, let's see here. Draw a picture. You're going to get this is going to be pi over here. Let's make this pi over 2. This is 1. So the y-axis on the left, and on the right, this is just in quadrant 1, the sine, which does something like this. Let's see if we can do this. And the cosine, which does something like this. So it's going to be this line and this line. But it's just this triangular region that it's talking about. No other place is a triangular region bounded also by the y-axis. You could call this teardrops or something, but it's just this region. Where does that cross here? Well, your guess might be pi over 4, and that would be good because both the sine and cosine are the same at pi over 4. So now we can go from 0 to pi over 4. The top function is the cosine. The bottom function is the sine. So the hard part about this problem is really knowing what they wanted in the region, and drawing a picture is the best way to do it. This, from 0 to pi over 4 cosine x dx, and this, 0 to pi over 4 sine x dx. So the antiderivative cosine is sine, evaluated from 0 to pi over 4, minus the antiderivative of sine is negative cosine x from 0 to pi over 4. Put in a pi over 4 so for sine you get square root 2 over 2. Put in a 0, you get 0. Minus, since we've got 2 of them here that might work, this is a negative cosine pi over 4, which is a negative square root of 2 over 2, minus a negative, the cosine of 0 is 1. Be careful of these negatives and stuff. It really gets confusing. So you really get the square root of 2 over 2. Well, this is minus a negative, so it's really plus square root of 2 over 2. And this is minus a negative, so it's plus, but we're subtracting on here, minus 1. So adding these two together, we get a whole square root of 2 minus 1. Okay. If you need more, make sure you ask. I sort of like doing these, and I need the practice too. That's section 5.6. Hopefully that's enough to get you through. Maybe that's too much. You don't have to watch the entire video if you get it before I get to the end. We'll talk to you later.